Hey, what's up everyone? Welcome to the stream. It has been a few weeks since I last streamed. Took a few weeks break, spent some time with the family, enjoy the summer here. But yeah, now it's time for me to get back to it. So, in fact, my last stream was one where I struggled to implement support for multidimensional arrays. After that stream, I did take some time to just sort of think about it, looked again at what I was doing, and I did come up with an approach that works. I don't love it, but I thought I'd share it with you anyway. It does work. Let me just show you what I'm talking about here. So yeah, there's two files. So this is basically the change for adding support for multidimensional arrays. So if we look here, the biggest part of this change is in my implementation of the LSIM array match. What was a lot simpler before, as you can see on the left side here, became fairly complicated, mainly because ultimately it's the difficulty here is trying to use regular expressions to do some kind of recursive match. And like basically this is let's say we talk about this as parser grammars. We have a grammar here that is recursive in its nature, and so that's not really the best thing to use regex for. Now I managed to find a way to do it with some logic in there. I've got some multi-match going on here, so that allows me to sort of iterate over portions of a very complicated regex and basically split out the information that I need. And ultimately what I'm doing here is I've got this idea of a vector of dimensions, where each dimension of an array, so this is like the idea of an array of arrays of arrays, right? So each dimension tells you its type, the max index, which is what's stored, and this thing called a type ref sim, which is something like a symbol definition ID, or symbol reference ID, I should say. Or it actually might be let's say for pointers, it'll be the typical type definition ID. So not pretty, but with a little bit of work, I got that going. And instead of returning, let's say for a single array, I was only returning, let's say the variable name is still the same, but previously I was returning, say, the type def ID, the index upper bound, and the LSIM type. These now have been put into this dimension structure, and I now return this vector by ref in a function called dims. So with that, I then was able to modify my RST parser. So when I know I'm matching an array, basically rewrote the code here so that I iterate through each dimension. Then for each dimension I do some parsing to figure out whether it's just a regular type or if it's a pointer type. And then ultimately I add array type here. So it's interesting because what ends up happening for arrays is that each dimension of an array defines a new type. So instead of storing, let's say, a single like in my debug info, rather than say store that, let's say, this variable is a multi-dimensional array of, say, 3 different levels, as far as it knows, it's store A is an array, and then the type of that array is another array, and the type of that array would be another array, and the type of that array might be int, you know? So that's sort of how it works, which is kind of nice, actually. It's somewhat elegant. It actually meant that I didn't have to add any support whatsoever to the way I display the information in the debugger, because everything just sort of works. You know, an array of arrays of arrays is the same thing as just a regular array in terms of display. So that's kind of neat. Now let me actually demo what this looks like. I think that's the fun part anyway. So here, for example, I have a multidimensional array named A. It is basically an array of 3, and this is also what I'm saying, right? It's a 3 by 4 by 5. So the way to think about this is you can think of it as the last one here, there is an array of 5 integers there. So that's going to be, there's actually going to be a type in my debug info that is an array of 5 integers. Then there's going to be another type, which is an array of the array of 5 integers that has a size 4. And then finally, there's going to be an array of that array that is size 4 of an array of 5 ints. And so that's basically what this ends up parsing out as. This code here simply initializes a counter and then basically goes through each dimension of the array and initializes the memory linearly with the next value of the counter. And then after that, we can take a look at what that looks like in the debugger. So say I hit F5 here. Now this takes a bit more time because I am running the debug build. I'm going to switch back to the release one soon enough. But it is much easier to debug when it's the debug build. Okay, so here we go. So I'm going to step in. And right off the bat, you can see on the left side, we've got our A variable here, which we can expand. And it is an array of 3, right? The inner one is 3, so we get 3 of these. Each one of these now can be expanded. And it's interesting because you can actually see the memory layout here. If I expand this one here, always the first address is always the same because, ultimately this is a single array, in effect, like a single buffer, just we're indexing it into 3 parts, but it's really one big buffer. And then you can see here, it expands, it expands, it expands, and then finally, the last expansion here starts to show us the elements of the array in memory. So yeah, you can see all that here. So this looks as you would expect. So let me just, we'll step in a few times. You're going to see how. Let's see here. Strangely, what just happened there? Oh, I think I didn't actually compile this. Give me a second. Looks like my stepping was on the wrong line. I'll try that again. So we go in. All right, let's expand this again. Just to sort of show. So here I'm going to step this line. We should see 0 appear here. The next time we step on this line, 1 should appear where the -101 is. These values, of course, are whatever garbage values are on the stack at this time. So that goes to 1, 2, 3. And I'm just going to hit F5 so we hit this breakpoint at the bottom here. So we're going to skip. We're just going to run through all that. And sure enough, you can see that all the values are being displayed correctly all the way until the very last one. That basically there was 60. The counter is 60, so the last element that got written was 59, which makes sense. Because last I checked, 5 times 4 is 20, times 3 is 60. So that looks good. So this is great, and I thought I was done. And then at one point I started hovering over my types, and I realized there's a small problem. It's not major, but basically, you see, like if in VS Code anyway, they don't display the types anywhere. You only really get them if you hover over it. So here, it's showing us that any one of these leaf ones here, the type of this variable is int, which makes sense, right? And if we go to the parent here, it's going to show us int of 5. Now this is correct, right? Because as we were saying, there are 5 ints. This is the type of this one here. Now where it starts to go wrong is when you go to its parent. You see how it says int 5, 4. It should say int 4, 5 actually. And then over here it says int 5, 4, 3. Now the thing is, the reason why it does this, and you can probably guess, right? This is an int, right? This is 5 of those. And then what ends up happening is we start, we're post-pending or suffixing the type name with the size of the array type. And we do that afterwards, which, logically makes sense, but when you read this, it looks weird from a C++ perspective. Ultimately it doesn't really make a huge difference, but it's not right. And I checked, and Visual Studio, doesn't do that. It puts it like reverses the types just to show you. I go to main here. Let's say we copy the same type here. I think I need to, okay. So we'll just build here, just to show you how the debugger, right, unreferenced. Okay. So yeah, here's the A, and you can see over here it says int 345. So that's really what we want to display, this type right here. And sure enough, as you expand it, you'll see it says int 445 here. You know, here it shows int 555, and then finally int. One thing I notice here is, at least for their expansion, they don't actually show like each level of indexing, which I mean, I guess we could do. But I think that actually that would be more difficult because I would have to go do some modifications to the way I display my arrays. So, I mean, I'm not going to bother. I think it's fine. In a way, I sort of like the way we display things because it kind of tells you exactly how you would get to that value. Here you'd have to do, you know, figure out yourself. Well, it's A of 0, you know. Whereas for me, not a huge deal. It's just a display thing. Let's see if we can get there. Yeah, so I have A, and then I have A of 0 here. They just put 0. And then when you expand this one, I put A of 0, and they'll put just 0 again. And they just keep doing that. I kind of like, I know it's kind of wordy, but I kind of like seeing the exact thing here. But I do want the type to be displayed correctly. I don't like the fact that we get int 543. So that's what I'm going to fix next. I actually took some notes about that. So where did I put that? Oh yes, it's in add array type. So here it is, to do. So if the type that we are creating an array around of, so that's what the idea here is. Add array type, we pass it the type def ID, and then we pass it the type that this is going to be an array of, and the number of elements for this array type we are creating. So if we are creating if we are creating an array of a type that is an array, so if type is an array type, then we are creating an array of array. In that case, for example, type name is int 5, let's say. And we'd like to insert our size between int and 5, so like int 45. Also, after this, it's time to make sure, so this is a separate thing. I have duplicated code in my resolve types right now for building the name of different types. So I'm going to want to fix that so I don't have to keep duplicating this code, especially now that I'm going to have something a bit more complicated than what I had before. So that resolve types, just to show you. Resolve types, debug symbols. Okay, so here's the function. So this is what I was talking about, where I have hack here, need a more generic solution. I'm basically duplicating, and this is the array part, I'm duplicating the way we name elements here when I'm resolving undefined types, just because I'm doing this later. And of course, this sucks, and I need to do this in one place, not repeat myself. So we're going to do that as well here. So, but let's just start with doing this part properly. So I think I'm going to have to do a little bit of string parsing here. So we'll start with if, what is it again? It's dynamic pointer cast. All right, so if the type as array comes in here, then we are creating an array of array. In that case, for example, type name is int5. I guess technically I don't even need the cast itself. I just need to know if it is, but unfortunately, the way to do that is with this. So anyway, we'll see. And then what we do is, I guess we want to search for the first open square bracket. Yeah. Think here. So let's find this here. This has to be valid, otherwise we're in big trouble. So let's say we make sure we found it, and then what we want to do is we would like to set our name equal to, let's see, the types. Yeah, so the substring, starting from 0 up until index, I think, plus this portion here, plus type name.substring starting from index. I think that's it. I might have an off by 1 here. Okay, otherwise, we just suffix our size to the existing type name. So let's say it was integer, we'd get int of, basically this is where we're adding the very first array dimension. So it's the normal case. And then here's where we're adding another array dimension. Okay, so let's see if this works. And we'll actually, we'll put a little breakpoint here. So I think the first time we should go into the else branch. That makes sense. So here our name is int5. That's good. It's all good. Now here's the second one. So now our type should be that of an int5. So here we are. We're going to do a find. We're going to get index 3, which makes sense, 0, 1, 2, 3. And we're going to try and set the name. Let's see if that came out. And there you go, int45. So that looks good. And then again, this is for the last dimension. Our type name is int45. We're going to find the index of the first one, which should be 3 again. It is. And we're going to set this one to int345. So now if I hit F5, okay, well, I can't actually continue from here. So let's do it from here. Take a sip of water. All right, so now let's see. There you go, int345 and int4 and 5, int5, and of course int. So everything looks fantastic. The other thing that's really cool is, by the way, is that this, I have an example here with simple integer, but it works even perfectly fine with structs, which is really nice. So if I just create here a little struct, a multi-dimensional array of structs, I should say. So f here is 2 by 3 foos, right? If we run this guy, let's see. Should I already see f in here? Count ijk. Kind of odd. Is it because oh, maybe it's because it's not being used. Yeah, I guess it got optimized out or something. All right, so let's use it. Just do something. F of 0 dot a. There we go. That ought to do it. Oh, I don't think I have my nice little functions here. So let's, I don't know. Let's copy a value. Hey, let's return it. How about that? Try not to get it optimized out here. Oh, not with the debugger attached. Okay, so there's our f. You can see that, well, we haven't actually executed that line yet, so let's get there. So f, there are basically 2 at the root, and then under each one of those there's 3. And you can actually see that the values are consecutive because I have a little global counter here. And every time we construct, it initializes a to the counter, and then it increments it, so we end up with consecutively allocated consecutive integers, I mean, in all these instances. I want to do this just to make sure that we're getting the offsets right for these structs, which we are. So there you go. And that's a foo. That's a foo of 3, and this should be a foo of 2 of 3. And there you go. So all that's working. I've also tested here with like more complex cases with pointers, all that stuff, and everything looks good. So this is half of the thing. Let me we need to insert our size between. I'm basically going to rewrite the comment above, but not as a to-do. When creating an array of array, insert our size between just before the type's name. Okay, so example. example, if type is int 4, or say int 3, is that what I had before? Int 5. And that's great, except that we don't want it here anymore. So what we want to do is we want to move the logic for naming something like this into the type itself, which might not be so trivial given that I have this add type function. Let me see here. Oh no, it should be doable. All I gotta do is move it into the constructor for array type, I believe. Mind you, is that correct? Here, I'm only changing the type's name. So if AT here is an array type, try resolve. Been a while since I looked at this code, so I just need to recursively try to resolve it. Right, okay, I remember now. This is for when types are unresolved, in which case we take the ID that's stored in the unresolved type and we say resolve it. And that returns a type. Now, if it's not that, oh right, okay, it's because outer types may internally contain an unresolved type. So indirect types, we try to resolve the type it points to, so that's for pointers. Array types may be an array of an unresolved type. Right, for example, an array of a pointer to some type. In that case, the resolve will be called here. And then that type gets resolved. But then we need to update its name, which is so crappy. Oh, right, because we didn't know. Yeah. Yeah, so not elegant. What would be the right, like, what would be an awesome way to do this? I mean, ultimately, I guess what we would have to do here is maybe have a, because okay, what we're doing is we're changing the type when we're resolving. Yes. This T here is passed by reference. So what we're actually doing is we are passing in the type, and then the type gets modified in place, which is a little bit weird, to be honest, but if we didn't do that, what we would have to do instead is return the type, which then means we'd have to like probably pass it as an output reference, something weird like that. But we in place resolve it, and that's why when we come out here, if the try resolve succeeded, that means that what was once here, this type here, which was once an unresolved type, has now become a new type that's been resolved. So our type has changed underneath us. That's where all this trouble comes in. And now it's going to say maybe what I'd want to do is have like a function called, you know, set type, let's say, right? But the thing is, I'm not getting back a type, like maybe something like this, but the type here is already changed. So if I had a set type, that might be a good place to do it. So it'll allow us to change its type, the type that it wraps. So perhaps I'd have to think of another way to do this so that I don't in place resolve types. Let me see if I could be smart about this. See, resolve returns a type. Resolve returns a type here. So what if instead of returning a type, it returned the type it's resolving or empty shared pointer? Then my try resolve could assign the result, and then I could do set type here. That might make some sense. But it would be so nice if I could do it through construction, but I wouldn't be able to, I think. Let me see. Right type, so all these types here. All right, let me try what I was thinking. And change that so it returns a new shared pointer type, but accepts one by const ref. Const ref here. I think I need to, let me try this. Let's be explicit about the return type for our lambda. What's going on? Oh, address of t it doesn't like, because we have a ordered set like that. Needs to be const here. So now if I say auto more variables to name here, which is not great. So we'll be like, we'll call this resolved type. So if we resolve the type here, then what we would do is we would say, like this, basically this is what we would want to do now, is like move the type in and replace the one that's there. And then ultimately we would do this with a function, and then the function could do the naming thing. But just to start off by making sure this works as before. And now again, this is where I really wish I had unit tests. I don't, and this is how you pay for the fact that you don't. Now what about here, struct type? Same idea. Okay, so let's just make sure this still works. See, I don't even remember my examples for making sure these get invoked. I mean, I know it has to do with for declares. I could probably find it. Just want to make sure I didn't break anything. Ideally, I would make this happen with let me see if I can. Yeah, let me see if I can get this actually to work with arrays. That would be ideal. Okay, so I've got some struct bar. I've got a pointer of an array of 10 bar pointers. Now I think I need to use this, otherwise it's not going to be happy. So let's say I have some function like, you know, whatever. Hopefully it'll actually allow this. Okay, compiled. See if I can see anything about bars in here. Bar. So B is a pointer 27, which is a pointer 28, which is a forward declared of type bar, of a struct bar. So that's what the X means. So that looks good. So I think this should be an unresolved type. And just to be sure, yeah, I've got all my breakpoints set. So let's see what happens. Okay. All right, so there's bars. 29. Okay, sorry, it's actually doing this part here. I was looking at, why was I looking at B? What is B? Oh, okay, that's the argument for do bars. Okay, so let me see here. Bars. There it is. bar 29. So type 29. So type 29 has already been defined as, no? No, let's just see what happens here. $29, sure. Okay, so this is the symbol type. There it is. Oh no, sorry. I was going to say that dummy is the part of it, but it's not. Okay, so we've matched. Here, define type. This should return a type that is an unresolved type. Perfect. Perfect. Although I don't seem to accept that, which is wrong of me. We should accept it because we allow for unresolved types. Why did I put that code there? No, that's what I usually do. Yeah. If type isn't found, create an unresolved type in its stead. These will be resolved later. So I shouldn't actually get an empty type. So let me see here. I think all these ifs actually are not useful, but it looks like we are we returning, or is it just a debugger? Oh, okay. That's confusing. So here we are. We're going to create an array type of an unresolved type right here. So type is actually unresolved. So we're going to create a very funny looking type that is basically just 10 because our name, it has no name. Really should put something there. I should put like unresolved so that we know that that's what it means. I'm going to do that right away. It shouldn't remain, but it'll help me debug like the situations where I don't resolve a type properly. And if I don't resolve a type, at least we can show it in the debugger as such. I think that would make sense. Guess I can't initialize type that way. This is what we should be doing here. For now, I'm going to put that because it's going to break all my code. But eventually, I'm going to put constructors everywhere and do this properly. Okay. right, so now it should say unresolved 10. Perfect. And I'm going to hit a 5. We're going to match a few more. What's this one here? Oh, these are just the other types. So I'm going to take off this one here. I'm going to keep going. All right, so here we are resolving types that have not been resolved yet. I have an array type. I don't know if this is the one. Let's see if we can see it. Yeah, this is the one, the first one. So our array type's type is an unresolved type. So this try resolve should return a resolved and it. This is why we debug things. What's the problem here? So we tried to call try resolve, and then it called resolve. Resolve called the resolver with ID 27. Oh, it's because I never defined it. Yeah, that's true. That'll happen. Let's, hopefully this won't actually fix everything. So we'll define it here. I think I had this problem where sometimes doing that ends up fixing everything. Hope not. I really should not assert there. It's valid. I mean, it's a linker error, but it's valid. I mean, it's not even a linker error. It builds, so I should not crash. So many things to handle. Okay. All right, here we are, about to resolve. Now it should resolve because it's, well, it should have anyway. It should have resolved because a type is present. ID is 28. Let me see. So bar is type 26. What's this 28 referring to? Huh. That's the first time I see that. $28. Hold on. Oh, I see. Right, because I'm not parsing functions and their arguments yet. Because I'm not parsing args. Like this stabs line here, I'm not parsing it yet. That's what it would imply. Because that is not an LSIM. See this 160 here? So because it's not a local variable and I'm not parsing arguments yet, I haven't registered the type for 28. So I can't use a function here. What can I do? I think if I just do this, it's probably not going to work because it's going to optimize it out as it tends to do even when I build and debug here. So here it still says 28. Parse 28, 30 is equal to star 26. Huh, you know what? It might just work. Maybe. It seems to be part of the main function here, so let's give that a whirl. I'll just do it from here first. See if it crashes. Oh, okay. Oh, and there you go. Bars actually shows up. Bar star. It actually sees what it is. Neat. I suppose if I added something to bar, it actually might work here. Let me see. Int bar value or something. So let's see if our expanded version of this array of pointers to an undefined type, defined below. Yeah, there we go. So now what should be incorrect are these types here, although it looks okay here. Oh yeah, because it's not an array of arrays. So bar star 10, that's correct. This would be a bar star. And then this would be a bar. And that's an int. Looking good. So I just want to verify that we step where I expect us to step in here in the resolving of types. Got to speed up this debug build. Too slow. Okay. So here we are. So now we did not resolve. Why is that? That was unexpected. Try that again. Looked like it was resolved. Oh. Oh, because it didn't need to resolve. So this is, oh, because of the pointer. Oh, right. Huh, that's an array of a pointer type. So the resolution won't happen on the array. I think I already faced this before and I forgot that making an array of an undefined type without using a pointer is very hard to do. I had it before though, didn't I? With this function here. Right. Why did it happen before? So if I have a bar star arg, then that creates that whole type, pointer to bar as an undefined type, I guess. Maybe. I wonder if there's another way for me to force it. Like if I just create a local variable called p here, maybe that'll change. See now p defines a pointer of type 26. Maybe this will work. Let's just see. I remember having a hard time getting this code to actually trigger like a few weeks ago when I was working on this. It's been a while now, but It's basically trying to force the debug info to give me an array of an undefined type. Not easy to do. Because it has to be through a pointer or reference. You can't make an array of a type that's not defined where it's not a pointer or reference, because the compiler would just fail to compile. It needs to know the size of the type. Alright, so let's see. Is this the case? No, it didn't work. It's still an indirect type. It's the indirect type that in turn has an indirect type. That's funny. I don't know if I can trust what I'm seeing here. So anyway, this resolution here doesn't do anything. I think what we'll find is that it'll happen here at some point anyway. All right, I can't do it for arrays, but it should work for the pointer type. So at least I should hit this one. Let's see if we actually hit this one. Should be resolving at least that one for the indirect type. No dice. Interesting. I think it was this code here. I'll see why that's any different from what I have though. P type 27 is a pointer of type 26. But you see it knows what bar is already. Yeah, this is what I ran into last time. The debug info still outputs the type for bar at the top of the file. doesn't change anything. Hold on a sec. All right. I was going to try this. Don't know if this is going to work. Let's see. These are builds. Yeah, it doesn't care. I remember I ran into this. I could not find a way. Oh, I wish I would have. See, if I had unit tests, I probably would have found a way to do this properly. I probably figured it out, and I think I can do it for data members, and that's what that example at the top of the file was all about. This one here. But this is the one case where I don't even have a name to adjust. Anyway. This is probably one of my least favorite parts of this code. Resolving undefined types. Okay, so this might be the case we just saw. Let me see. So this should be unresolved. And what is my type? So this is a top level unresolved type. and then it becomes an indirect type called forward. Yeah, exactly. So here we go. So forward right now, do forward declaration. So we only forward declare this type. Bar contains a pointer. So this is the case where a struct has it in there. So just that case alone. Oh yeah, that's right. Using a struct with another forward declare of another type seems to do the trick. That's the way to do it. Okay, that's good. Okay, at least I have a case here that I can actually test. And then here, this is what I was saying, is that I have to set the name here to name star, just like I would do if it had not been an undefined type. So what we want to do is we want to change this so that I basically have two ways. Either we do a set type or we recreate our type, but the recreation is a bit annoying. So let's go with set type for now. Plus star, right? Okay. So that would be, so we would change this now instead to it set type, and then we'd move this type in. Similarly, when we create our indirect type, let's do it with a constructor now. Whoops. Okay. I'm going to start doing this with constructors, and slowly but surely we'll clean this code up. So you see how here we're doing make shared indirect type, and I was doing this manually. Now we won't do that anymore. Instead, the name will be computed automatically, and we'll just move type in there. That builds. So let's debug this, make sure everything looks kosher. Odd. Why did that behave differently this time? Or did I remove my... Oh, okay. That's why. I removed my breakpoint. There we are. So now we're going to take here, we're going to go inside there, we're going to move. So see, type right now should be an indirect type. I can't even tell. Why isn't it? That's odd. Type star. I feel like I can't trust this debugger at all. What the hell is going on here? Oh, it's because we moved it. What the hell? I swear. Can't understand anything. Debugging has become very difficult. Ironically, I'm writing a debugger. But debugging the debugger is not easy. This looks right. Somehow when I'm debugging this, it doesn't seem right, but it does look like it's working. I think it's because it's just that same problem where Visual Studio has a difficult time debugging lambdas, I guess. That's all I can think here. It's very strange that I can't see these types in the debugger. I wonder if like disabling optimizations has some effect even for debug builds, which is weird because debug builds disable optimizations, but I am noticing some weirdness. Let me try this. it's generating the CMake cache. Hit F5, so this should build again. No? Okay, there we go. It's starting to build. This is going to take a little while, unfortunately. But it's all right. Hopefully this will make debugging actually work for me. Okay, almost there. All right, build succeeded. Let's launch this succeeded build. Okay, any better? Let's see. So this is an indirect type star. It has a type, and for some reason, once again, so that did not help whatsoever. Very strange. My only guess is because we're under a lambda here. It does seem to be some issues of Visual Studio debugging lambdas. Maybe. Forward star. So here at least we can see what's going on. But when I'm out here, forget it. Debug info is all messed up. Yeah, don't know. Anyway, I'm convinced that this is working. I'm gonna actually keep going, and we'll do some testing, see how it goes. So we're going to want to do the same thing now, of course, for array type. And I guess for struct type. Yeah, that makes sense. So here we're going to take a type, and we're going to take a number of elements. Just wondering what I want to do here for when I have more than one thing here. Okay, yeah, I guess we'll do the same thing. Set type. Okay, and now we do type again equals to move t in there, and we're going to copy the code for setting the name properly, or move the code I should say, in our add array type. Whoops. I can actually leave it like this. Yes. Okay. So setting the type also sets the name, and the number of elements is set as well. So with that in place, we now go back to debug symbols, and we do the same thing. AT in this case. Type. That there. And in the RST parser, all of this code will change, and we now pass it the type and the number of elements here. All this disappears. It's nice. Code's getting much cleaner. Bit by bit. Okay. And finally, we do the same thing for structs. Now structs is a bit more annoying because it's actually not the struct itself, but the members of the struct that will change. Let me take a look at that again. It's going to be a little less clean than what we've got. Where's my struct type? Here it is. It is actually a case where the member name doesn't change, but let's look at add struct type. So normally when we do this, we, right, because we get a vector of members. Yeah, this one's a bit funny. Huh. All right, let's go the other way this time. Oh yeah, in this case we actually give it the type name as well, which is also different because a struct has a type name that the user defines. That's right. Okay, that's cool. We have a type name, we have a byte size, and we have a vector of members. I think I'm going to have to move this up. And I think here we're just going to call it name. That's what we call it everywhere else. So that takes care of that bit. The only part that's a bit not awesome is the creation of members. Okay, so let's do it again, like I was saying, one bit at a time. So here this becomes type name followed by byte size followed by a move of members so that cleans up that part. But before that, we were creating members here. The name of data members has nothing to do with the type in this case. I don't know. I'm on the fence about adding a set type here. It doesn't seem to make a lot of sense. In any case, it's not like we are doing anything with the name. We're just moving a type in there. So I think we can leave this alone for now. But I will keep the fact that we have a constructor, so that's a lot better. Really, we should do it for the rest at that point. And by the rest, really I only mean primitive type and noon type. And then there's variable. But yeah, for those that derived from type, those are the only ones. I guess I could do that while I'm at it. So let's say primitive type here. Yeah, this one has a few more members to worry about. Let me go see here. So name is signed and byte size. That's pretty much it. All right, let's do that. Oh, what about format? Oh, we set the format down here. Okay, yeah, we need the format as well. Format is signed byte size now for the name type name So this means is that for format, we're going to want to figure out the format first. And now we can construct our type here. Actually, I could totally do the format myself, shouldn't, inside the type, since it's part of the type name. Yeah, maybe I should do that. Push that code a little deeper. Yeah, let's do that. We'll remove format here. I'm like on the fence here. Okay, yeah. I kind of like it better if we figure it out ourselves. All right, that's looking good. So this cleans this up. Now there's add enum type, which really has name assigned, byte size, and value to ID. So all of this now we can actually see all of these functions at once, which is pretty nice. Almost making them obsolete, but not quite. All right, let's just do a quick test here. I do really need to write some unit tests. Maybe I should start streaming that. Maybe the next time, that's what I'll do, is start working on some kind of unit test framework, because this is getting bigger and bigger and I have like less and less confidence in my changes. Okay, this looks all right. Oh yeah, this is the cyclic. This basically goes on and on forever. Similarly. Lovely. There we go. Nice staircase of infinite recursion. I mean, I may as well just do the last type here, I think. Let me see. Name, type, location. I think we create variables. Let's just take a look here. I think I make them in multiple places. Yeah, in the DAP debugger, I make them here. So maybe I'll wait for this one just so that I don't have to go changing this file right now. But not that it should be very difficult. But we'll make that a separate thing. We'll just have refactored all the types that derive from type. Okay, great. Symbols, all looking good. All right, pretty happy with these changes. I think we can get this committed. It's a lot of changes for actually something that seemed very small initially. So I'll say here, fix type name of multi-dimensional arrays. And I'll just say AG for int 345, we were displaying int 543 as the type name of A. Fix this. Fixed. Fix this also. so that all type-derived classes are constructed. Also added set type functions to and array type so that they can properly set their name field based on the type they it's always weird, on their type. This allows us to remove the duplicate type name setting, the duplicated code in would be nice if Git extensions did text reflowing the way Vim can do. Actually, I think I can remove this now. This default type that I had. Let me go take a look. Now that we've added constructors everywhere, I think we can. Yeah, just array type needs to explicitly pass it no name. And there's a bit more. I should remove these const string refs here and move the names up the chain to be consistent. better. Oh yeah. Unresolved type will have name. Now have name unresolved, which will help to, which will be useful at debug time if any type names are left unresolved. Mind you, I think I don't even handle unresolved types, but like I don't really display them. I probably should. Anyway, whatever. Okay. I think that's everything. All right, so this would be a good place for me to stop. That took a bit longer than I thought, to be honest, but we did do quite a bit of cleanup, refactoring, which I'm happy about. Obviously, there's still more to do. So in terms of what's next, what I will be doing, apart from the general cleanup, I still have so many things I could work on. I don't even know. Like one major type I'm not supporting yet are unions. That's on the list. There's still a few little bugs that I'd like to handle. So here's my massive to-do list. Yeah, stuff like this. I'm gonna have to move some of this down. And technically this is done now, which means support for arrays is done. So this is what I was saying. Add support for unions, add support for type defs. Okay, like this was something we saw. Don't crash assert when undefined. What is that? What I call them? Undefined type. Unresolved types are not resolved. This is valid. For example, I don't know, pointer to an undefined type in a single compilation unit. So like this is the part where we probably want to display this type. Mind you, after compiling other compilation units, we'll probably resolve it and display it, so that's okay. Display unresolved types in the debugger in case we never resolve them and or to help debug, to help realize when we've forgotten to. This is all cool. A big part of me is starting to feel like I want to work on this though, the write unit tests for the DApp debugger. So I thought about this. I think I may have even spoken about it before, but the idea here that I have in my mind is to write tests. So I wrote here, each test will need a small source file sample that is compiled to an RST file, or more than one. Then the test passes the file through the RST parser and validates that the debug info contains what we expect. we'll probably want a script to compile each test sample to produce update RST files. Yeah, the only thing I don't like about this is the fact that I would need to generate a file. But I sort of don't have a choice because I need to call the compiler, the fork of GCC there that I'm using to compile this for every test. So, you know, most likely I think what I'm going to probably do is, well, either I'm going to create source files like I said and literally just run them through it, or my tests will contain source in like a raw string, and I will write that to a file, compile that. Maybe that's better because at least then there's no files on disk to manage, and those files I create can just be temporary files. Plus, we would see the source in front of us for what we expect, which I like as well. I'm going to say here, instead of so source code should be in raw strings, and from which we create temporary CPP files that we compile. Yeah, that may be a bit annoying with how the make stuff works, but we can figure this out. Actually, it's probably even easier this way, because I think then what I can do is I can blast those CPP files at the end of the test, so the next test can just reuse the same make file, and the make file will, I think I can make it just discover, or maybe I can generate the make file. I don't know. I'll figure this out. Surely we can do this in an elegant fashion. It does mean invoking the compiler from C++, which is maybe a little less cool. We need to invoke make at runtime, but also need to possibly generate a make file or make it pick up. I think actually it already does that. Let me double check. Yeah, I don't actually have to do that. Okay, so never mind that. It's because the alternative would be or create a script to compile each test sample. So this would be the idea that we actually have like some master script, and the script just goes and takes source and compiles each one and then runs the test or something. I actually think that's less elegant. I prefer doing everything within the unit test. So yeah, so this means like I'm going to probably use Google test, and yeah. This could be interesting. I mean, I'll tell you one thing is once I have a bunch of unit tests to test all these different cases, man, I would feel so much more comfortable with the refactorings and the changes I'm doing. And I'm probably going to discover a whole bunch of corner cases and bugs that I need to fix, which is great. I don't really think I can get around it without having unit tests. I can only program as a cowboy for so long. So maybe that'll be the next thing to work on. It could be interesting. All right, so I'm going to stop here. Thanks for watching, and should be back in a couple days on Thursday. So Thanks a lot, and I'll see you next time.